Mason is a frequent star on our peer learning network. Seth, thank you for joining us again. He's going to talk today about R2Cross. And this is, again, a little bit of a continuation from what we started diving into at the October workshop that we had in Avon. So yeah, Seth, I'll just turn it over to you, but we're really excited to hear your presentation, and I'll let you take it away.
Okay, thank you. I did want to, hope you can all see my screen. I did want to let you all know that I'm happy for you to interrupt me as I go through this. We can save questions for the end if you like, but if you want to just stop me midway through, hop on, unmute yourself, ask me a question, I'm perfectly happy with you doing that. I think the recent question and Chris's answer to it are probably a useful starting place for introducing this topic, but this is a continuation of the conversation that we began at the last peer workshop in October related to flows and thinking about how you develop thresholds, or if you aren't going to develop thresholds, think about kind of relative changes in flows as a function of planning scenarios or given projects, and how you use information related to those changes in flows to talk to a group of stakeholders about what those might mean for changes in the condition or the characteristics of other environmental attributes that you might care about. So one of the things that we talked about very briefly in that conversation, one of the methods that we talked about was R2Cross. And the group then asked me to come back and dive into R2Cross a little bit more and provide you all with a sense of what that method is, what the information, what information you can derive from implementing this method on a stream reach of interest, and then how you might use that information in the context of a stream management planning effort. So that's the adventure that we are undertaking here for the next 20 minutes or so. So I plan to spend a little bit of time talking about the technical foundations, the kind of background of the method itself. We'll have a little segment of the conversation that focuses on the actual methodology. I understand that most of the folks on the call today are unlikely to be the ones out in the field performing an R2Cross analysis, but hopefully having a sense of what those methodological steps are will give you some important background as you think about hiring somebody to go collect data in your watershed. You think about the kind of scale and level of effort involved in this particular method, or where existing data might be available to you that was produced by this method, et cetera. And then at the tail end, we'll talk real briefly about the use of outputs from R2Cross in a planning process. So to begin, it's useful to reflect on the fact that R2Cross is just one of any number of methods, threshold setting methods specifically, that can be used to kind of pin specific stream flow levels to maintenance of an environmental condition that you might care about. There are a number of other methods available to you that have been put in practice in Colorado and in other streams across the West. We are, again, focusing on R2Cross today, but the focus on that method, I don't think is meant to preclude or suggest to you that you should not consider the use of other methods. The intent really is to help you understand how the method works, so that you can, if you are going to go out and either hire somebody to do this on your stream, or maybe you're going to go out and collect data yourself, that you're doing it in a kind of a responsible manner, and that you're generating defensible and widely acceptable information from it. And then also providing you with some sense of the limitations of the data, so that you can use that information most effectively and most prudently in your decision-making process or in your planning process. Okay, so at the last meeting, we talked about these different approaches to doing flow-related environmental and recreational needs assessments. Like we're missing, there we go. We talked about risk rating approaches that are based on varying degrees of hydrological alteration. This is the watershed flow evaluation tool variety approach. We talked about environmental flow threshold setting methodologies. R2Cross fits there. We talked about environmental response function development. This is something that you see in places where you might be developing a PHAB sim model, for example, 2D habitat models. And then we talked about the methods used for relating flows and changes in flows to recreational use opportunities. So we're limiting our discussion today to this consideration of environmental flow thresholds, and we're not venturing into the discussion of the methods that fit in these other boxes. And then within here, we are further restricting ourselves to consideration of R2Cross again, which is just one method that you can use to identify environmental flow thresholds. So we're real focused here. That's the point. There are some basic assumptions of the R2Cross methodology that are worth reflecting on here. Those are that riffles in a stream are critically important channel units, and they're places in the stream where you tend to find high levels of macroinvertebrate production. They can be important for spawning for various fish. They're important because of the macroinvertebrate production levels. It's important feeding grounds for trout. And so they're worth focusing on as you think about environmental flows. There are also locations where during low flow conditions, you would tend to expect the greatest change in velocities and depth, and that these channel units, these positions on the stream, are going to be more limited, or that the access to these locations is going to be more limited for aquatic organisms than in other channel units like pools and runs. Maintaining adequate stream flow in riffles then is expected to maintain adequate stream flow in those other channel units in pools and runs. So why use R2Cross instead of the other approaches that might be available to you? The approach itself is pretty time and labor efficient. You can go out and you can quickly collect data on a reach that you're interested in and turn that information into a threshold, a flow recommendation. The results produced by this method have been found in the past to be comparable to more complicated methods like the in-stream flow incremental methodology, where you're implementing something like PHAB sim, doing 2D habitat modeling. The method itself is widely used in Colorado, so it's endorsed by the CWCB. It's used by CWCB and CPW to as the basis for many, but not all, in-stream flow water rights across Colorado. And there are available tools to support the use of R2Cross. And the link here is to a web application that I think many of you may find interesting and or useful as a basis for just exploring the method in greater detail or actually performing an R2Cross assessment. For the next few slides, we're going to talk about the details of the methodology itself, how you would go about locating a site, collecting data, analyzing that data, and identifying thresholds. So the first step in that process is transect selection on your reach of interest. So you've got a reach of stream that you're considering. Within that reach of stream, you've got different channel units. You've got pools, riffles, runs. And if you are seeking to implement R2Cross, you need to seek out riffles, not the other channel units. And ideally, you're identifying kind of a typical riffle within your reach, something that looks representative of other riffles in order to collect a single transect. You may, if you've got time and available funds, you may select to collect data at multiple transects and not just one. in your reach of interest. There are some things to avoid, including braided channels and areas with undercut banks. If you were to collect data in those locations, you would find your results to be probably unreliable. So this is just a picture of what a riffle looks like. It's the shallow, steep sections of the river, the places that you could imagine becoming drier quicker, shallower quicker as flows drop. Once you've selected your riffle or riffles, you go about collecting data on them. The data that you're after includes cross-sectional geometry. So you go out with an optical level or a sag tape or a total station or some other means of survey, and you collect elevation information across that transect. Then you additionally need to collect water depth and velocity information on that same transect and collect a stream discharge measurement. And all of that information together provides you with the necessary inputs to one of the optional analysis techniques that you can use, hydraulic analysis techniques you can use within this method. Optionally, you can collect particle size distributions using a Woolman pebble count or some other means, and that opens up the number of hydraulic analysis methods that you might use in the subsequent step. If you are somebody who is working with the state for the state on a new in-stream flow right appropriation, you may be necessary to conduct a new fish survey or collect macroinvertebrate samples. I think for most of you, this last point here, this collection of biological data will not be necessary, and you will instead be relying on existing CPW survey data or perhaps the new aggregated macroinvertebrate data from Riverwatch to inform how you're thinking about the structure of biological communities on your reach. Okay, so you've got these these topographic and hydraulic data sets, and you are now in a position to do some hydraulic modeling. There are two different approaches that you can use to do this hydraulic modeling. One relies on the Ferguson equation, the other Manning's equation. Probably don't care too much to know about the details of either, but if you did go about collecting particle size distribution data, sediment data from your transect, then you can use the Ferguson equation. If you didn't, you need to use the Manning's equation, calibrate a simple one-dimensional hydraulic model, and then run that model across a range of discharge events. So you went out and you measured channel characteristics discharge at, for example, 100 CFS. You want to know something about habitat conditions, not just at 100 CFS, but at 10 CFS and 50 CFS and 150 CFS and 200 CFS. Well, you could go out and you could directly measure those characteristics at each of those flows. That's pretty labor intensive. The shortcut here is we use these hydraulic modeling techniques to approximate conditions across the flows that we did not observe in the field. So we collect the data, we calibrate a model, we run the model over a range of flows that we didn't observe directly to approximate those hydraulic conditions that we care about, which include average water depth, average water velocity, and wetted perimeter of our channel across some range of stream flows. Once we have that data in hand, we combine or we reference a table of relevant flow criteria that comes from some publications in the late 70s that have been recently kind of updated and modified. So we've got these flow or these criteria related to the depth of water in the stream, the percent of the wetted perimeter, and the average water velocity. We look across our simulated flows and the hydraulic characteristics associated with those flows. And then we identify the flows where those conditions are satisfied. Traditionally, the flow where 2 of the 3 criteria are satisfied is used as the winter minimum flow in an in-stream flow water right. And the flow where 3 of the 3 criteria are satisfied is often used as the basis for the summer in-stream flow rate. That is not the rule. That is, it's just something that plays out often, and you might consider using that information in the same way. Okay, so you've got flow targets now associated with this satisfaction of 2 of 3 criteria and 3 of 3 criteria that kind of represent different levels of protection, perhaps, for environmental attributes that you care about on your reach. You need to then integrate that into your planning effort. So with this information in hand, you can do several different things. And we touched on some of this in the last workshop. You might set out to evaluate those thresholds against existing or historical stream flows in your reach of interest or across your watershed. And by comparing your flows across some period of time against those thresholds, you can calculate in a pretty simplistic manner the deficit, the environmental flow deficit on the reach you're interested in. And that deficit can be calculated in terms of acre feet, can be calculated in terms of durations, the number of days that meet or fail to meet your environmental flow threshold. And those relative differences, if you're looking across a geography, can be really useful in helping you do some priority setting regarding which parts of your large geographic area you're going to focus on. And those computations might also be useful for thinking in a specific location about, they might be the basis for discussions about flow augmentation or flow leasing, or some consideration about where opportunities might exist to help meet some identified environmental flow deficit. Alternatively, you might think about using some of the scenarios that come out of the technical update to the water plan to project forward how environmental flow deficits might change as we move into a different climate future, a different population growth future. And that's kind of what you're seeing here. You would, in the same manner as we just spoke about, compare those environmental flow thresholds to flows, typical flow conditions realized under each of the flow scenarios that come out of the technical technical update to the water plan. That comparison might give you some sense of, as we move into a very hot and dry climate future, if we're worried about that, how conditions might change on your reach of interest that would be, supportive or detrimental to aquatic biota and to other attributes that you might be concerned about. And there's some pretty simple ways that you can graphically represent that information and use it as a basis for talking to a group of stakeholders about which of these future scenarios is worth kind of planning around or hedging against, and what opportunities might exist to you to avoid some undesirable future state. The last pathway that you might take as you consider using these thresholds in your planning effort is to use them to characterize the potential benefits or impacts of a specific project or management action. And you do this, again, in a similar way, where you would need to characterize the expected impacts of a management action. Maybe that's an augmentation strategy or flow leasing, or maybe it's reservoir development. You need to characterize the expected impact of that action on stream flows in your reach of interest, the reach where you've got targets, these flow targets identified. And then characterize the kind of typical hydrograph for the existing condition and that future condition, and compare the flows across some period of time, the year, a season, a month, to the threshold that you've identified, your 3 out of 3 threshold, your 2 out of 3 threshold, and compute the kind of duration and magnitude of the gap between the flows under that condition and your environmental flow threshold. So those are 3 ways that you might think about incorporating use of thresholds into your planning process. That's not, those are probably not the only ways you could go about doing that. I'm sure some of you are very creative and could imagine doing it differently, but I think that provides you with a sampling of where you might go, how this information might be useful to you. I'll leave you with some thoughts, some important considerations regarding the use of these thresholds that come out of R2Cross, and this kind of applies across any of the threshold setting methodologies. And that is, that these tools are a heuristic. They're not a panacea. The thresholds that you derive from R2Cross are really intended as the kind of minimum flow levels necessary for protecting aquatic life in a reach. They're not probably not the optimum flow level. There's no guarantee that if you manage flows to these levels at a specific time of year, or certainly across the entire year, that you would preclude any undesirable changes to the aquatic ecosystem. Or you can imagine and pick your local stream. I would guess that it's probably a snowmelt dominated system where you have a high peak in the spring. If instead of having kind of a normal shape hydrograph where you got a peak spring runoff followed by low flows in the late summer or fall, if you had a flat hydrograph that was always pegged to the R2Cross threshold, I imagine you could convince yourself that would produce some changes in your aquatic ecosystem that might not be desirable. So it's a useful benchmark. It's not the answer. There are other characteristics, right? There's peak flows, there are rates of recession, there's variability between different parts of the year that are really important considerations because they do impact the structure of the aquatic ecosystem and certainly would lead to changes in those attributes are expected to change conditions for aquatic life. And then there are those other non-flow related characteristics that are important not to lose sight of. Water quality characteristics. You might have a great hydrograph where you're always meeting the in-stream flow and you've got an old mine dumping metals into the stream, and doesn't matter how you're managing flows, you're never going to have a great fishery because they can't live there. Water quality is crap. Same goes for riparian condition. That might be an important limiting condition for the aquatic ecosystem before flows are. Stream temperature, although often related to flows, might be limiting before flows are limiting. And so, you don't want to lose sight of some of these other things. You don't want to lose sight of the bigger picture and rely too heavily on a threshold coming out of one of these methods. But as one of the tools in your belt for helping you make good decisions within the context of a management plan, and certainly as a tool that is inexpensive to implement, is widely used across the state already, it can be a really useful means for facilitating conversations about flow needs for aquatic ecosystems, and about the relative benefits associated with any proposed project or management action as it relates to those aquatic ecosystems. All right, I'm at 23 minutes. And I think I had 25. So that's your really brief overview of R2Cross. I'm happy to answer a couple questions if you have any.
Seth, I got a question, and I guess one comment too. I appreciate your presentation. This is great. I think this should be the bones of a lot of SMPs as you develop it. one thing we ran into is be cognizant of existing ISFs on streams where you're doing R2Cross and putting that information on a sheet of paper. Coordinate with CPW as you're doing that. My next question would be, Seth, what are you finding the most reliable tool to evaluate, required stream flows and sort of high gradient step pool systems? As we're starting to get out of the main stem, starting to get up into the headwaters, right? That, some of us are looking at a little bit more discreetly now. R2Cross being based upon a riffle, can be tough sometimes and give a lot of variation in data points. What are you utilizing?
Yeah, I think you hit the nail on the head there. It really is kind of site dependent, depends on the characteristics of the given stream, but something like residual pool depth might be a more reliable means. Those systems might be places where you might rely more heavily on the historical or the kind of natural flow characteristics of the reach to inform what the ideal characteristics of that reach would be. No single answer for you, Scott, but yeah, that's a good question.
We found we're getting into 1D and 2D pretty fast just to sort of look at a lot of the numbers, but then you start to get cost with survey. And so maybe it's just a comment too. As you start to get into high alpine, it's a little harder to find a number to hang your hat on, but great presentation.
Yeah. And I think that, that some of the assumptions and that go along with R2Cross, right, that, that riffles are an important area for macroinvertebrate production, that they are kind of the limiting channel unit for fish passage, probably aren't as relevant or aren't as applicable to a step pool system, right, where fish they're not kind of leisurely transiting through a step in a step pool, they're jumping it or moving over it very quickly. You don't have high levels of macroinvertebrate production in a step pool system. So I'm not sure that this would be the best method to apply in those real steep settings anyway.
I think we've got time for one more question, and I see April, you have your hand raised.
Thank you. I think this has been really helpful. I wanted to ask, maybe Seth and Nicole and Chris, who are familiar with several stream management plans, something that Seth kind of hinted on, that these in-stream flows don't always address all of the issues on the stream that we're working on. And so thinking about it from the Water Quality Control Commission hat that I was mentioning, how often are the stream management plans looking at water quality issues and how those are affected by flows and can be affected by flows, particularly those water quality issues that are coming? We know that our standards are changing, and the dischargers, how often are the dischargers involved in the conversation, and the community around this stream thinking holistically about the changes in standards and the ability to meet those? I'm thinking mostly about temperature and working those issues into stream management plans as well.
I can just say so I am very involved in the work up here in Northwest Colorado, and we did a stream management plan that Seth was involved in on the 9 miles of the Yampa River just through Steamboat Springs, and the city led that. And one of the big reasons that the city did that was because they wanted to identify the relationship between water temperature and flows, because they were having exceedances at the wastewater treatment plant. And we then sort of took what the city did, and we've now expanded it to 350 miles of the Yampa. And I think that focus on temperature has really remained. We are developing a basin-wide temperature monitoring plan as one of the recommendations of our stream management plan. So we're going to start collecting more temperature data in more places and have a centralized database for that. And there's a whole riparian shading component that we're going to be working on as well. So I can say, at least up here, there's a big focus on temperature. Carrie, Dennison, I'm not sure what you guys are doing in the Gunnison, and if that is the case there.
Yeah, thanks for bringing it up. I think it's incredibly important to understand the relationship between flow and temperatures and other water uses. We've had some monitoring specifically on the Big Cimarron River over the past few years. Notice that we've been hitting even CWC in-stream flow rates, even on really bad years, but the temperatures have been so high that we've wiped out populations of trout. And so we need to understand and have a better correlation between temperature and flow. So flow isn't everything if it's being interrupted and we're relying solely on return flows. But more temperature monitoring, the better. We are also tracking that on our some of the process-based restoration work we're doing in our headwaters and on Escalante Creek, and understanding that flow isn't everything if those temperatures aren't conducive to maintaining aquatic life. Thanks for bringing that up.
All right, great. Thank you guys for taking the time to answer that question. And thank you, Seth, for that presentation. I know that was super helpful for everyone. And Russ and your team, and Nicole also for your presentation.